Hi, my name is Avin,
And my name is Avantika.
and we are tackling Sustainable Goal 11, Sustainable Cities and Communities. Our solution is the Agrotech drone, which we will be talking to you about today. These are the 4 things that we will be covering in this video. An increasing population means that more food needs to be produced in order to meet the increasing demands of households. This demand, however, can only be met by greater agricultural practices. But as a result of mineral leaching, as well as increased carbon dioxide due to decomposing organic matter and the formation of acids in the soil, soils tend to become too acidic and infertile for crop growth. This can lead to a serious issue of food insecurity.
Food insecurity is the lack of access to enough affordable and nutritious food. This can lead to malnutrition, which creates a domino effect of other problems, such as high mortality and infection rates. Rates of food insecurity are rapidly rising due to farmers not being able to keep up with an increased demand of food. This issue is also being worsened by COVID. At the beginning of 2020, 135 million people faced acute food insecurity. By the end of 2020, this number is expected to have almost doubled to 256 million. Therefore, safe, efficient, and effective agricultural practices are needed to ensure access to clean, nutritious food. A key aspect of this is fertile soil, which we will talk about next.
Soil fertility is defined as a physical or chemical problem in the soil that inhibits or prevents the growth of plants. This can include things like soil with a poor physical structure and therefore limited access to oxygen and water, or a chemical imbalance of nutrients in the soil. Our solution tackles soil acidity and dryness. Globally, each year, an estimated 24 billion tons of fertile soil are lost due to erosion.
To sum up, the problem we aim to address is inefficient agricultural practices leading to soil infertility, which can result in global food insecurity in an increasingly urban population. Our solution, which specifically tackles the issue of acidic and dry soil, is a land drone with a control sensory system that measures pH and moisture levels in the soil.
The process of our solution follows this logical structure. Using our code that we will show later on, the drone will be able to map its path by dividing the field measurements given by a farmer into 25 equal-sized blocks. It will move along each block and perform both a pH and moisture test. If either of those measurements are outside its allowed range, the block will be colored red, and if both tests are within the allowed ranges, the block will be colored green. The farmer is then given a full report with the exact location of the red blocks using a visual diagram. Meanwhile, sprinklers will be activated in the areas where the blocks failed the moisture test.
Now for a closer look into the drone. It comes with wheels and a control sensor system that includes pH, moisture, and infrared sensors. The pH and moisture sensors sample the soil at equidistant intervals and convert their data into a digital format. This digital data is sent to a microprocessor, which checks it against stored values. If the soil is too acidic or too alkaline, or too dry or too moist, a warning signal is sent back to the farmer. If the soil is too dry, a signal is also sent to an actuator, which prompts the activation of a sprinkler near the dry soil. The infrared sensor is used to prevent the drone from crashing into plants or other objects.
Here's a simplified model of the land drone which we designed on Fusion 360, a computer-aided design software. The pH and moisture sensors can be found at the bottom to maximize efficiency of the testing. Both sensors are connected to a mechanical arm which can extend further to penetrate the soil beneath it in cases of uneven soil, and the holes found on each side of the drone will be fitted with an infrared sensor.
This is some sample code we've written using Python to visually describe the output of the drone. The first part of the code shows the farmer inputting the dimensions of the field, which the program divides into 25 equal sections. The drone travels to each individual section and performs the necessary checks. If the checks produce values which are in an acceptable range, the section is colored green. If not, it is colored red. This provides a visual as well as written report for the farmer. We will now run the code to show you what happens. The first values that we are inputting are outside the given range. The soil is at a pH level of 5, which is too acidic, and a percentage moisture of 30. This is infertile soil and therefore represented by the color red. The next patch of soil has a pH level of 7, which is neutral, and a percentage moisture of 50. This is fertile soil and therefore represented by the color green.
In the sample code, the values of the pH and moisture levels are inputted by the user. However, in the actual solution, values from the sensors are sent directly to the microprocessor, with this code eliminating the need for the farmer to check individual values.
To take it one step forward, we would fit the top of the drone with a solar panel to increase the running power, sustainability, and efficiency of the drone. Secondly, we would add gas sensors and humidity sensors to test air quality and moisture in the air. Lastly, the drone could be equipped with tools to do chemical tests on soil to determine the level of nutrient ions, such as nitrates, that are present in the soil.
Thank you for listening.